Hey everyone, welcome to this video. It's on graphing rational functions. First of all, I want to draw attention to my shirt. All right, it's Friday, so there's no kids at school, so I got to dress casual. It's The Office shirt, Bears beats Battlestar Galactica. If you don't know about The Office, then we need to speak immediately so I can enlighten your life. All right, but more mathy stuff now. So this week we're talking about, and next week too, talking about graphing rational functions. This week we're talking more about the algebra stuff, right? So where it says the algebra side, right? So we're looking at the graph without the graph. So we're gonna use algebra to figure out key characteristics of the graph, and then next week we'll actually be graphing using those key characteristics. Okay, now there is a graph on here because I need to introduce you to some vocabulary words. So let's look at it here. So I have a graph on the paper. Let's see here. Here's my XY chart. And this is what the graph looks like. And like this. All right, very rough sketch, but kind of like that. And it's f of x equals 1 over x. Okay, so this is the parent function. Remember, parent function is where all the other rational functions come from. This is the parent function, 1 over x, right? So you can see it's a rational function. It creates a fraction, and the x is in the denominator, which makes it a rational function, right? The rational equation, whatever you want to say. Or with this notation, it's a function. So the first word we're going to talk about is the hyperbola. Now I know it's out of order. I'm sorry. When I was deleting stuff for this year and copy and pasting some stuff over from other years, I put it in reverse order. We're going to talk about the name first. So hyperbola. Not to be confused with hyperbole, right, which is another vocabulary word that I don't know what it means. I've heard it used before, but I don't know what it means, hyperbole. Maybe you can tell me. Anyways, hyperbola is the shape of a rational function graph, or of the graph of a rational function. So the shape of the graph, so this right here, this shape where there's kind of like almost like a parabola, but not really, on this side, and then on the direct opposite side is that same shape. It's almost like a reflection. That's the hyperbola, and it's always going to look like that, very similar. Sometimes it'll come in a little deeper, or it'll be super wide out here. Sometimes it'll switch, so I'll have the graph here and here, right? So things like that, those are transformations. But they're all going to have that same generic shape where you have this and this. There are some, and we'll talk about this next week, and we'll kind of introduce it this week with the algebra side, but we'll talk about it more next week. There are some where there's some stuff in the middle here between these two. But for right now, we're not going to worry about that. We're going to worry about that next week, okay? So this week, this hyperbola is kind of the shape of the graph. Every hyperbola or every rational function, the graph of a rational function, has a vertical and horizontal asymptote. Sometimes there's more. There can be more than one vertical asymptote, but there's always at least one if you're going to get this hyperbola. Now a reminder, an asymptote, and you can write this on your paper. That's why I have it here. But I have a space for you to put it in case you've forgotten, but I'm not going to, maybe I will. I'll write it down for you. Remember, an asymptote, okay, is a line. It can be a vertical line or a horizontal line. It can also just be a slanted line, but we're not going to talk about those this year. We don't have time. So, a line that the graph approaches but doesn't cross. Okay, so an asymptote is a line that the graph will approach, but it will not cross. You saw asymptotes in SM2, or SM3, with exponential graphs. So, for example, here, notice that this graph gets really close. It's approaching this line right here, y equals 0. But it doesn't cross it, but it'll approach it. The graph also approaches this line, this dotted line that I have here. It approaches it, but it never crosses it. X equals 0. Okay, and we draw our asymptotes with dotted lines. The reason we use dotted lines is because they're not real line, they're not actual physical lines that we've graphed. It's displaying that it's an asymptote. Okay, but not a physical line that's been graphed like a function. Now these will change, and I'll show you the patterns and how we find the vertical and horizontal asymptotes. But there will always be one. Okay. If there's not a vertical asymptote, then it's not going to be a hyperbola. It's going to be a different graph, something reduced, and it'll be a different graph. Okay. So here's the two new vocabulary. Well, this one's not really new, but here's a new vocabulary word just to kind of get us started. Let's move on to the next part. Actually, I'm going to keep this up. Talk about the next part. We're going to talk about the asymptotes. Okay, there's a reason that the vertical asymptote is 0 here, especially x equals 0. Now remember, an asymptote is a line, and so if you don't put x equals 0, if you just put 0 as the asymptote, means nothing. Means nothing. It's a line. It's x equals 0. Here, y equals 0. That line is an asymptote. It's y equals 0. If you just put 0, means nothing. So make sure when you write down your asymptotes, you need to put x equals a number, y equals a number. All right, the reason that this is the asymptote for this function, what happens if I plug in 0 for x? I divide by 0, which we can't do. So the graph can never be at x equals 0. The graph can never be there because it would cause us to divide by 0. That's why the asymptote here is 0, x equals 0. Because if x equals 0, then we divide by 0, which we cannot do. And so the graph will never cross there. Okay, it approaches it, it gets really, really close. We can plug in 0.000001 and not divide by 0. And we can plug in negative 0.000001 and not cross because we won't get a 0 here. But the actual specific exact value of 0 we cannot have because then we divide by 0. That's why it's a vertical asymptote. Okay, now the horizontal asymptote. The reason it's y equals 0 is because of long division. Okay, that's actually where we get our horizontal asymptotes, is from long division. If I were to do long division with 1 divided by x, I would get 0 as an answer, and I would get a remainder of x. Or, excuse me, 1 divided by, I get a remainder of 1, sorry. Right? So let's see here. This is going to look kind of weird. It'll be easier later on. And I'm going to show you a pattern to where you don't have to do long division. But if I did 1 divided by x, well, 1 goes in, or 1 times what gives me x, it's also x, right? But it goes in 0 times because we don't know what x is. So we don't know if it really does go into it. Well, let me leave that back up. Sorry. And so it comes from long division. Okay, we get, first, that's wrong. It's this. That's why it sounded weird when I explain it. 1 divided by x. Okay, so x times what is 1? Right, well there is no integer that gives us that. Okay, it's actually 1 over x, which is our original. So nothing will give us 1 because we don't know what the number is. Right? And so nothing in mathematics, when we subtract 0, remainder 1, nothing in mathematics, we use the number 0. All right, so it actually comes from long division. I know it's a little bit hard to see. I'll show you 3 patterns of how to find the horizontal asymptotes, but it comes from long division. So if you forget the patterns, when in doubt, use long division. Anyways, that's why we have y equals 0 as our horizontal asymptote. And so this graph will never cross y equals 0. Okay, the other reason for it, it comes from long division, and that's how you're going to get the patterns. I also want to show you this too. Y equals 0. Y and f of x are interchangeable. They're synonyms, right? That just means the output value. So let's come here. I want to find where y will equal 0 for 1 over x. Is there any x value that will make 1 divided by a number equal 0? No. The only way with fractions to get 0 is if the numerator is 0. For example, I'm going to erase this real quick. Let's say 0 over 6, 0 over 7, and let's say 4 over 5. You can put this in your calculator if you want. This is why I've been telling you need to practice fractions, because we've been using fractions a lot. 0 divided by 6, 0. If I have $0 and I distribute my $0 among 6 friends, how much money do they each get? 0. 0 divided by 7 is 0. 4 divided by 5 is 4/5. If you want a decimal, 0.8. So notice the pattern here. The only way to get 0 when you divide is for the numerator to equal 0. That is the only way. But here we have a 1. Does 1 equal 0? No, it will never equal 0. That means that this fraction will never equal 0, so the horizontal asymptote will never be 0. Or the graph will never intersect with y equals 0, because y can never equal 0. That's why there's an asymptote there. Just like x can never be 0 because we end up dividing by 0, y can never be 0 because we can't have 0 in the numerator to make it 0. And that's why we have the asymptotes there. Okay, we'll talk about this more. We're gonna do some practice problems right now. Okay. Now I want to go over real quick the patterns with you for the horizontal asymptote. Okay, the vertical asymptote isn't too bad to find. Essentially, what we do is like we just did with 1 over x. We set the denominator equal to 0, and that's our horizontal asymptote. Or the vertical asymptote. Man, I keep getting my words mixed up. I'm sorry. Let me restart. To find the vertical asymptote, we just set the denominator equal to 0 because the denominator can't equal 0. So if we know where it does equal 0, that has to be an asymptote. To find the horizontal asymptotes, there's a couple of patterns that I'm going to show you. Okay, so pattern number 1. If the degree, so remember degree is the biggest exponent in the polynomial. So if the degree of the numerator is less than, specifically less than, not equal to, less than, the degree of denominator, then y equals 0 is your horizontal asymptote. And like I said, this comes from long division. Okay, when you do long division, you end up getting a constant on the top, and so the constant will never equal 0 unless it is 0. But then if it does equal 0, then it wouldn't be a rational function. Anyways, 2. If the degree of the numerator is equal to the degree of the denominator, then y equals leading coefficient divided by leading coefficient. Okay, remember leading coefficient is the number that's touching the variable that has the largest exponent. Now, don't worry, we're going to do examples with this, I promise. So if the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is y equals leading coefficient divided by leading coefficient, or leading coefficient over leading coefficient. And you probably saw this one coming, number 3. If the degree of the numerator is bigger than the degree of the denominator, then no horizontal asymptote. So if the biggest exponent in the numerator is bigger than the biggest exponent of the denominator, there is no horizontal asymptote. There is an asymptote. It's called an oblique asymptote. Sometimes you'll hear slant, but that's an informal word. The formal word is oblique. But we're not going to cover that this year, just for time's sake. It's instead of a horizontal line, it's a slanted line. That's why sometimes people call it a slant asymptote. Okay. Just like always, you're going to want to fully factor, right? You're not getting away from it this year, and I reminded you that. But if it helps, fully factor the denominator to find the vertical asymptotes, because there could be more than one. So sometimes you're going to have to factor. So let's look at the second page. Here at the second page, let's do these four together. Okay, so we want to find the vertical and horizontal asymptotes. So the vertical asymptote, we set the denominator equal to 0. So x equals 0. Hey, we're done. That's my horizontal asymptote, or vertical, my vertical asymptote. Horizontal asymptote. The degree of the numerator is 0. There's no x's, right? There's no x values in the numerator. So the degree is 0. The degree in the denominator is 1, right? X to the first power. So the degree of the numerator is less than the degree of the denominator. So we go back. That's situation number 1. So my horizontal asymptote is y equals 0. And there are your answers. Okay, let's do the second one now. Oh, wrong page. Okay, so vertical asymptote. I set the denominator equal to 0. Okay, and then let's get x by itself. So x equals -3 is the vertical asymptote. The horizontal asymptote. The degree of the numerator is 0, right? There's no x's, so x to the 0 power. The degree of the denominator is 1. The biggest exponent is x to the first power. So degree 1. The degree of the numerator is smaller than the degree of the denominator. So y equals 0 based on our patterns that we just went over. Okay, here, vertical asymptote. Set the denominator equal to 0. Add 5 to both sides to get x by itself. X equals 5 is the vertical asymptote. Horizontal asymptote. The degree of the numerator is 1, and the degree of the denominator is 1, so they're equal. The degrees are equal in the numerator denominator, so it's leading coefficient. Y equals leading coefficient here, so it's a 2 over leading coefficient, which is a 1. So y equals 2. 2 over 1. Okay, so here, vertical asymptote. We set the denominator equal to 0 and get x by itself. So x equals 5/3 is the vertical asymptote. Horizontal asymptote. It's degree 1 over degree 1. So that means y equals leading coefficient over leading coefficient. So 1 over 3. And there's your horizontal asymptote. And that's it. Okay, next week, like I said, we'll graph it, but I'm worried more about right now how to find it because these are level 2 questions is finding it. The graphing are level 3 and level 4. That's why we're going over next week. But the most important thing to pass the class, can you find it algebraically to receive a good grade, like a B or an A? You need to be able to find it on a graph kind of thing. So we'll talk about that next week. Okay, let's talk about the next thing. Now, remember at the beginning of the year, I started talking about how we don't cancel things out. And I said that we talk about it later on. Why we don't say cancel out, we say reduce. Well, this is the point where we're going to start talking about it. Is why we don't say cancel out, why we say reduce. And it comes in the form of a hole in the graph. So, let's look at the f of x equals x squared minus x minus 2 over x squared minus 5x plus 6. Okay, let's fully factor like we've been doing. Maybe something will simplify and it'll be easier to work with. So x minus 2 times x plus 1 over, let's see, x minus 2 times x minus 3. Oh, hey, look, the x minus 2 and the x minus 2. I'm going to say cancel out just so you can see why we don't cancel out. The x minus 2 and the x minus 2 cancel out. Hey, it's simpler. It's easy to work with now. It makes my life nice and easy, right? No. Because they didn't go away. Okay, the reason why teachers say cancel out is just to show you that we're actually multiplying by 1. Okay, this is why I'm telling you that if you say cancel out, it's setting you up for failure because of this point right here. These don't cancel out. When you divide something by itself, it's 1. It doesn't go away, it's 1. Right? 3 divided by 3 is 1. It's not nothing. So in fact, what I'm actually doing is x minus 2 over x minus 2 is 1 times x plus 1 times x minus 3, or over x minus 3. But 1 times anything is itself. That's why we say reducing. Because it didn't go away, it's still there technically. And you're going to see why. So, right here I have x plus 1, x minus 3. What if I plugged in x equals 2 to my equation? Well, over here, if I plug in 2, I get negative 2 as an answer. But what if I plug it into the original? This is the original. This is what I'm graphing. It just kind of simplified to this. Well, if I plug in 2 to the original, I divide by 0, which I can't do. So what the heck just happened? Why can I do it here? Why can't I do it here? It's because of that reduction. Okay, the reduction simplifies the graph, but it doesn't take away this point that creates the 0. It just simplified the graph. And in fact, this point right here, this x equals 2, it creates a hole in the graph. And like I said, we'll talk about this more next week in the actual graphing, but I'm going to put it up here for you. So let's say I graph this, x plus 1, x minus 3. Okay, now this is off the top of my head. This isn't the actual graph, but it's just to convey something to you. So here's my hyperbola. Okay, and at, x equals negative 2, excuse me. At x equals negative 2 on the graph right here, there's actually a hole in the graph. Okay, so the whole graph is this right here. That function is what's graphed because it was a simplified form. Everything simplifies out to give us this graph. But from the original, we still can't plug in x equals -2. Sorry, that should be +2. That one's -2 when I plug in the +2. I still can't plug in. Oh, okay, let me restart. 1, 2, there's my hole. At x equals 2. So here's my hole. I still can't plug in 2 to the original because I would divide by 0. But what's graphed is simplified form right here. That's why there's a hole in the graph at x equals 2. It's saying, here's my graph. Everything works except that 2 because in the original, it causes us to divide by 0. That's how we find a hole. Okay? Essentially what it is we find out what factors reduce to 1. Which ones reduce? And those factors that reduce, we set them equal to 0, solve, and that gives us where our holes are, x values. And then we plug it back into the simplified form to find the y values, because that's what's graphed. The simplified form is graphed. Okay? I know this is a lot. Let's practice it. Which time we're at. Doing good. F of x equals x squared minus 2x minus 3 over x squared minus 3x minus 4. We're going to factor. Now notice x plus 1 and x plus 1, they reduce, they do not cancel, they don't just disappear, they reduce to 1. Anything times 1 is itself. So we're left with x minus 3 over x minus 4. Now the whole. Remember, these just didn't go away. They reduced to 1. So if I set the factors that I reduced to 0, x plus 1 equals 0, and get x by itself, that's the x value of a hole on the graph at -1. Now remember, the actual graph, the picture of the graph, is this. It's the simplified form. So if I want to find where the hole is on the graph, I got to find the y value too. Right? Remember, location is an x and a y value. That's why we did the math history with Rene Descartes. Okay, with finding the flies on the ceiling. Because we need an x and a y value. If I plug my x back into the simplified form, that will give me my y value that's on the actual graph, or on the actual graph. So I'm going to plug in -1 for x. So my y value is 4/5. This is the hole in the graph. Okay. If I were to plot this, and I gave you room at the bottom so you could draw this with me. Let me find my, let's find the vertical asymptotes and horizontal asymptotes and graph those two, huh? So vertical asymptote, I look at the simplified form, set it equal to 0. X minus 4 equals 0, so x equals 4 is a vertical asymptote. 1, 2, 3, 4. Horizontal asymptote, degree 1 divided by degree 1, so leading coefficient divided by leading coefficient, y equals 1. That's my horizontal asymptote. Okay, and my graph is kind of like this and like this. Okay, once again, with the graph, they're always going to be in opposite corners like that. And we'll, like I said, we'll talk more about that next week, but they will always be in opposite corners like that. At x equals -1, there's a hole in the graph. Okay, and that's how we draw it. I'm going to bring my computer a little closer just so you can see it. So hold on. There we go. So you can see at x equals -1 right here, there's a hole in the graph. because at x equals -1, it creates the original function to divide by 0. Okay, so there's a hole in the graph, and that's how we draw it. Now I know the hole is bigger than just the location. It's okay. We're doing it exaggerated so that we know that there's a hole there. All right, let's do the other ones. So we have f of x equals -2x plus 8 over x squared minus 6x plus 8. I'm going to fully factor. So -2 x minus 4 over x minus 4 times x minus 2. The x minus 2's reduce. So I'm left with -2 over x minus 2. So on my graph, I'm going to draw a graph here. Vertical asymptote. X minus 2 equals 0. So x equals 2 is the vertical asymptote. Horizontal asymptote. The degree in the numerator is 0. The degree in the denominator is 1. So the numerator is less than the denominator. So y equals 0. Is our horizontal asymptote. Okay, our hole. Well, we reduced x minus 4. Set it equal to 0 to find the x value of our hole. Plug that number, the x value, back into the simplified form. So -2 over 4 minus 2, which is -1. Okay, so there's a hole at 4, -1. Okay, so my graph is going to kind of look like this. And at 4, -1, there's a hole in the graph right there. Okay, let's do the next one. F of x equals x squared minus x minus 12 over 2x squared minus 4x minus 16. So this is x minus 4, x plus 3, and this is 2. Let's see here, minus 2, that's minus 8, so minus 4 plus 2. The x minus 4 is reduced. So I'm left with x plus 3 over 2 times x plus 2. So my vertical asymptote. Set the denominator equal to 0. 2 times x plus 2 equals 0. Divide everything by 2. X plus 2 equals 0. X equals -2. One, 2. Horizontal asymptote. The degree in the numerator is 1. The degree in the denominator is 1. So it's leading coefficient divided by leading coefficient, which is 1 over 2. So y equals 1/2. So let's say this is 1, so 1/2 is about right there. Let's find our hole. Well, the factor I reduced was x minus 4. Set it equal to 0 to find the x value of your hole, which is 4. Plug that back in to the simplified form. Maybe I shouldn't do that. So 4 plus 3 over 2 times 4 plus 2, which is 7 over 12. So 7 over 12. So our graph is going to kind of look like that, and like that. At 4, there's a hole. At x value of 4, there's a hole in the graph. Okay, last one. So fully factor 2x plus 1 times 2x minus 1 over so that's -6, and so we want -3, +2. Okay, there's your factor. 2x minus 1 and 2x minus 1, they reduce. So simplified form, 2x plus 1 over 3x plus 1. Vertical asymptote. Set the denominator equal to 0. X equals -1/3. I set it equal to 0 and solve. Horizontal asymptote. Degree is 1. Degree is 1, so they're equal. So leading coefficient divided by leading coefficient. Y equals 2/3. The whole. We reduce 2x minus 1. So set that equal to 0 to find the x value of your whole, which is x equals 1/2. Plug 1/2 back in to the simplified form to get the y value. 2 times 1/2 plus 1 over 3 times 1/2 plus 1, which is 2 over, this is 3 halves plus 1, which is 5 halves. So it's 2 over 1 times 2 over 5, so 4/5. Okay, if needed, do that on a calculator. So let's see, -1/3 is vertical asymptote. So here's 1. So here's -1, or -1. There's -1/3. Y equals 2/3. So here's y equals 1. So 2/3 is about there. And our graph's going to kind of look like this. So at 1/2, x equals 1/2, there's a hole in the graph right there. Okay, so algebraically, how you find the hole is you fully factor everything, reduce, and those factors that you reduced, you set equal to 0, and that's how you find the hole. Okay, finding the vertical asymptote, take the simplified form, set the denominator equal to 0. To find the, I just said horizontal, right? Okay, redo. You're going to see very soon, every single year. I don't know what it is with me, but for some reason my head mixes up vertical and horizontal, like the words itself, not the asymptotes, not the pattern, but just the words that get twisted in my head. So I'm going to start again. We talked about the whole. Vertical asymptote. Set the denominator of the simplified form equal to 0, solve for x. Horizontal asymptote. Look at the degrees, and on your paper here, the very first page, it has the patterns. Degree in the numerator is less than the degree in the denominator, y equals 0. Degrees are equal to each other, y equals leading coefficient over leading coefficient. The degree in the numerator is bigger than the degree in the denominator, no horizontal asymptote. Okay, and that's it for this video.